This was the talk I gave actually at the University of Michigan about 3 months ago. Then I retired in the meantime, but I thought, well, this is as good to go here. I have to mention, if you want to contact me and check the papers, that's my forward address. If you want to contact me, this is my now active address. I have a bunch of people to recognize there, but I was told this is going to be shorter presentation, so I'm going to go fast through this. I apologize. Fairly technical. Again, I apologize. Send me an email if you have questions. OK, here is a question. You saw the title of the talk, right? Why would anyone want a feedback loop to be unstable? In my long career, no one ever asked me to make a feedback loop unstable. However, there are examples, right, of unstable feedback loop. Biology and economics, of course, a lot fewer in engineering, but flip-flop is unstable system. Nuclear chain reaction unstable. Here in multi-agent systems, it turns out that there is a relationship between fluidity of motion, right, liveness, and stability of the loops created by the agents. And this is what we found. Let me move this in your way. Gridlock possible, stable interagent loops. Gridlock avoided, unstable. Faster instability, more graceful passing. So we want instability. In fact, we want fast instability if we can have it. So how do we get to this? OK, there is a lot of work to get to that. So first, I want to talk about computational complexity. So can we have these multi-agent systems as a convex optimization problem? There is a big difference, you'll see in a moment. Then I'm going to introduce control barrier functions. Illustrate this on a vehicle experiment. I'm going to go talk about multi-agent system and holonomic robots, review some CBF-based algorithms, show Monte Carlo simulations, and then the key part of the talk is towards the end when I am explaining the results with the stability analysis. Negotiations is actually this stability versus instability, and illustrate this with more complex examples than the analysis is done for. So I'm packing a lot of stuff into one slide here. Apologies. Why CBFs? My shortest answer I can provide is because I get a convex quadratic program. As Rockefeller said, the great watershed in optimization is between linearity and nonlinearity, but convexity and non-convexity. If I have a convex program, I have favorable scaling with the number of agents. Number of agents, it's linear if I have decentralized. So if I only take care of myself and ignore everyone else, assume they are going to keep doing whatever they are doing, they are not agents, right? Then it scales linearly with number of agents. If I have a centralized system or co-optimization, theoretically, number of agents to the power 4. But actually, we observed number of agents scaled for number between 4 and 32. This is interesting because 32 agents, 4 and 32, were done with human in the loop experiments. So I can run 32 agents in real time because humans obviously require real-time computation on a workstation. I don't think you can do it with anything that looks like this. So alternatives. You can see everything is NP hard, all the other options NP hard, meaning essentially really difficult. Discrete search is officially exponential, but whenever it says NP, you can say it's pretty much exponential. Now, I can't talk too much about this. There is a lot of, these are just review articles that I'm listing there. So if you want to review, the last one has, I think, 120 pages. So you can read a lot about this. But obviously, I have to go on a tangent, actually. So the tangent here is control barrier functions. I have system dynamics, could be nonlinear. It's important that it be linear in the control input. I have admissible set. So here I say, well, I want to keep my, let's say, vehicle or robot above the water line, right? I don't want my robot to go down, which is very appropriate given the situation in California. So you don't want the robot to be submerged. So you have to keep it where h is greater than 0. And this h is the control barrier function if I can find u such that h dot plus lambda h is greater than 0. Think about what it means for a moment. I have an obstacle here. I'm moving towards it. Let's say the distance is h. It's decreasing. The rate of decrease should be proportional to the distance, but not faster than that. If you can control the constant lambda, then you pick that lambda, whatever is appropriate. In any case, there are two alternatives here. The other one is kind of if you don't have a constraint on u. Basically, if you lose control over h dot, you want what remains to be positive. And it's relatively recent, 2007. So basically, if I have an h, I can find u such that this is satisfied, or in other words, that this is just a chain rule formula, right? That is satisfied, greater than 0. If I can satisfy that, then h of t is greater than h of 0 e to the minus lambda t. So I guarantee if I start with positive h, it stays positive, right? Pretty good. Important thing is the constraint is affine in control. So when I set up this way as a quadratic program, so someone comes in, this is a CBF-based safety filter. So if you give me a control U0 that does whatever performance you want, right? It goes to the destination, for example. And there is a constraint. Let's say there is a water there. It says stay out of the water. That's the second one. You say, okay, I can do this. I need to solve this. I want control as close as the original, which satisfies the given constraint. This is a quadratic program. It's a convex. It's nice. It's easy to solve. The important thing is no additional tuning parameters. I really have nothing to tune. This is it. So if H is a CBF, I have some guarantees. QP problem is feasible. The resulting control is Lipschitz continuous, which is important. You'll see in a moment with the importance of continuity. I guarantee, obviously, H of x stays greater than 0. Local stabilization property and some mild technical assumptions are inherited from U0. So if you come close to where you want to be, to your destination, then U0 dictates what happens there. Now, let's talk about robustness. So I have this, I'm allowing, you saw that, I'm allowing H of t to go down to 0, meaning I'm allowing this to approach the boundary of C. Well, what if I have disturbances or uncertainty or something, right? What can I do? Well, I can actually move this a little bit, make this h of x a little bit smaller, right? Basically shifts it down and shifts it a little bit away. What happens if I do this? What happens is once I cross this new boundary, there is a restoring force pushing me back out. So if I have small disturbance, I need small eta, if you want, to have this region small. If I need large disturbance, I need to move it farther away. Basically what happens is I have a trade-off. I'm getting the robustness, but my obstacles got bigger. If I make them really big, well, maybe I will not be able to move around, right? If every obstacle is huge, then there is no path around. But there is a trade-off there. A little bit finer, let's say a little bit more precise handling of this is if I put a disturbance there and I have some model and the disturbance looks like that, right? It enters there as a W. I know some limit on the disturbance. So I can define a robust control barrier functions. Basically, it's the same thing as before, except I have put my worst case disturbance there. So it says, even in the worst case disturbance, I can use control U to guarantee that H dot plus lambda H is greater than 0, greater or equal to 0. So if and this is actually, the definition actually comes from my paper, in contrast to most of the other stuff, right? So combining these RCBF with the baseline control, I can do two things. I can use worst case disturbance, or maybe somehow I know the disturbance, or I partially know the disturbance. In this case, I assume I pretty much know the disturbance. I can plug it in, right? So either satisfy first or second. And so this is the robust control barrier function. The second one is going to play a role subsequently. Turning obstacles into barriers, well, and now how would you do that, right? You saw that drawings for the barrier functions. It was obviously non-convex, but it doesn't matter for the barrier functions. I treat them the same. There is only one tuning parameter. It's easy to generate barrier functions. Let me show you this. You have a Roomba robot. You say, I don't want Roomba to hit the wall. Well, there is a line there. The equation of the line x plus by plus c equals 0. My barrier function for the wall is just that. That's it. If I have a leg of the table and I know the radius, I can say, OK, keep that hc greater than 0. If I want to have some, so stay a little bit more away, I can make it a little bit bigger, use a barrier margin, right? Say, OK, make this radii just a little bit bigger, so you're going to stay another 2 inches away from either the wall or there. If I have, and in most cases it will be the case, higher order system, it's not a problem. We handle it with a higher order barrier constraint. There is again a little bit of technicality with the now the feasible set C now including H dot, but that depends on what lambda you use. But then anyway, this can be done too. In any case, you can see it's not too difficult. It's fairly straightforward. You say there is a wall, there is a desk, there is something else, there is another Roomba robot, no problem. Okay, so we have done all this. We have done all this in experiments, right? Pretty much. So these chairs that you see there are actually just circles, because this vehicle stays away from the chairs, right? First step is U0. There is a path planning, start point, target, waypoints, pure pursuit. Very straightforward, right? Then someone comes and put chairs there. Well, we control steering and braking, so you can see how that works. This is all real time, not sped up or slowed down. This was COVID time. I was actually in Michigan, virtually present in the vehicle when they were doing the tests. So they were moving the chairs, and sometimes it would go around both chairs on the same way. Sometimes in between it, you saw that. Looks more impressive from the inside because the steering wheel turns quite quickly. Because you need to turn, at low speeds, you need to turn the wheel a lot to get this much steering. In any case, works. Now to the kind of starting the second half of the presentation. How about these chairs are not chairs, but they're other agents. They have their own idea what should happen, right? How about traffic? You can see here, right? It's traffic in Paris. Well, tell me, can you predict what others are going to do 2-3 seconds in the future? Probably not, unless they're stationary. Then the motorcycles come, and that gets, so you can see that, right? Anyway, this motivates our, okay, no precedence, right? No rules, right? It's not like, oh, these guys coming from the right, they always have right of way. It's, yeah, well, maybe, but not entirely. Sometimes we humans do produce gridlock. You can see one here. So we are not perfect. Avoiding interacting obstacles, a lot of work done on this. There is optimal reciprocal collision avoidance work with the velocity cones. One interesting thing to know there, it's 2011 paper, it splits responsibility between the two parties to avoid, and there is no third party in that calculation. So the third-party constraints are absent. We call this decentralized reciprocal. It's reciprocal because you take half of the responsibility, don't take other counterparts, obstacles into account. Another interesting thing is frozen robot problem. You can see here uncertainty cones of the people walking, and if that robot up in the corner, if you ask the robot to actually move in between them, it's probably not possible. There is no way you can find it. So you basically say, okay, I have to start moving to create path for myself. And this is done by optimizing for everyone. And we refer to this as co-optimization. So you optimize for yourself as well as others at the same time. The last set of papers is control barrier functions, and they consider centralized, decentralized follower, decentralized reciprocal. These are our names. It's got centralized is theirs, but we call these algorithms decentralized follower and decentralized reciprocal to make it clear what we are doing in the subsequent presentation. So here, back to Roomba robots, and we have these multi-robot problems. They are all agents. They all have a simple dynamics, second order, right? Positions, velocities, accelerations. Distance-based CBF, I already said what I would do. This is just the distance. I add a little bit of a radius margin. Doesn't play a big role in this presentation, but it does. It's in the paper for other reasons. So if you compute the second order derivatives, you get something on the form aij plus bij ui minus uj, and you want to keep that greater or equal to 0. That's a barrier constraint. So each one of these generates each two agents generates a pair of constraints, which means that scale about number of agents squared. You can see the formula there, right? If I have 10 agents, I think 45 constraints. It grows quite fast. Decentralized multi-agent controllers. I'm doing okay, I think. No common communication protocol. Each agent computes its own best action. No co-optimization, no planning for other agents. So here I have, I know why, okay, sorry. Decentralized follower simply says, okay, I'm responsible for avoiding collisions. There are no guarantee of collision avoidance because they are too optimistic on the passing side. Once aij goes positive, they think they can take the full kind of a slack to 0. But if both decide to do that, then they collide. You can see that here. Decentralized reciprocal is nicer, actually, as long as the QP, and you can see QP, actually, there are a number of agents there, and it could be 10 agents. As long as it's feasible for everyone, they are going to avoid collision. However, it may be infeasible, and you can see an example here. The one from the left, one from the right are moving. The one in the center wants to be stationary. But both moving ones assume stationary is going to move because it takes half of the responsibility, right? But it can't. There is no accounting for third-party constraints in this. You can see that, right? I optimize only my own constraints with other ones and ignore their problems, right? So here it becomes infeasible. They crash. Centralized, this is a good one, right? It requires communication. The central node computing everything knows everything, computes for everyone. We guarantee collision avoidance in particular because we can guarantee feasibility. And this is one feasible action. So proportional braking for everyone is a feasible action. It's true even if these robots are non-holonomic. The same thing applies. Feasible action is proportional braking. If you have a limit on acceleration, then you have to limit the speed relative to your lambda k you pick. K equal 1 or 2. Either one would work, but you have two eigenvalues. These are minus lambda 1 and minus lambda 2 are eigenvalues of that second order equation. I mean, characteristic values of the second order equation. So, co-optimization. Tesla, 2 years ago in AI, they said, well, you need to plan for ourselves and everyone else jointly. We call it co-optimization. But basically, you optimize for everyone. You have to be aware if other ones have constraints. But this gets complex pretty quickly, right? And I think they use discrete search. And I think they also use some kind of a neural network to kind of get this into the feasible, pick most likely scenarios, and then only study those. That's what I think, based on what they said. In any case, here, in my case, I just have a complete control set strategy. It has everyone's constraint available. However, it doesn't have other agents' desired accelerations because it doesn't know what U0s are for the other ones. Doesn't know where they are going, right? So basically, this is the two actually makes it guarantee collision avoidance for two agents. For more than two, it does not. But we kept two because at least if the problem is only between the two, this guarantees that they are not going to collide. Otherwise, they're going to collide even with two agents. This is the structure of the algorithm. It takes position and velocities, computes both, uses its own, throws out the other one, discards the other one. And this I bring up because there is another algorithm which says I compute this for both, the same thing except for W's, what you saw before. There is no two. We don't need two for this Predictor-Corrector for collision avoidance or PCCA. This is, again, our paper, 21. This is the structure now. So we use the robust control barrier function. You can see two W's, so there are uncertainties, right? I say, OK, there is a disturbance. Do I know the disturbance? How do I know the disturbance? Well, I could take what I computed. Oops, sorry. I can look at what I computed, compare it to what I measured the other one do, say the difference is the uncertainty, feed it back. I need a unit delay or filter to break the algebraic loop. Otherwise, I have algebraic loop. So I can guarantee certain things for this. Again, feasibility I get. I control everyone in my world, in the ego vehicle world. I control everyone, not in reality, but feasibility doesn't depend on reality. It depends on what I'm giving myself as the degrees of freedom. WRs are bounded if these differences are bounded. So as long as the distance and the relative velocities are bounded, W's are going to stay bounded. I have, interesting, regardless whether both implement PCCA or only one implements PCCA, the other is non-interacting, I can prove that the h of t stays greater than O of delta t means something that goes to 0 with delta t. So the faster I sample, the smaller this thing gets. So basically, delta t, think of it in the delay I get the information in. The shorter the delay, the better off I am. But this is obvious, right? If I have a delay in getting information from the other, I'm going to potentially collide because it's always late to where the other agent is. So, but this tells me that if I sample fast, I only need a epsilon radius margin. So here is what we compared. You're going to see Monte Carlo simulations. Here I have centralized. Decentralized fall over reciprocal, complete control set, PCCA with sample delay, and PCCA with low pass filter. This one, I think that on the right. By the way, initial final destination random, non-overlapping. So you just pick them around, say, OK, you go to wherever it is. Except for centralized, the other ones use only observed quantities. There is no exchange of information. This one, I think, is the worst case for one of the PCCA. You can see how this goes, right? This is one that took the longest because they are facing one another, I think, directly on at one point. But anyway, they resolve it. These are the results. Too much, but I'm just going to show you these two things. This is important. First of all, let me show you that indeed the violation is small for the centralized PCCA and 2 PCCAs. And indeed, if you increase the sampling, we show all of these disappear. And then let me also show that number of gridlocks don't coincide with the co-optimization versus decentralized. Co-optimization does not solve the problem of gridlocks. You can also see here is the max time. And you can see the 3 on the bottom, they're almost agreed, are centralized and 2 PCCA. There's very little difference, and very little difference from run to run. So you can see while the other ones obviously have large variation. To combat the barrier violations, you can make them bigger. Obviously, it plays no role with the three good ones. But for the centralized and CCS, they kind of grow bigger, but they also slow them down significantly and increase number of gridlocks. Deadlock resolution. So you have this, people looked at this, right? In particular, the CBF-based one, there are some things. They usually consist of 2 steps. One is identify deadlock situation, and then once it's identified, you execute the prescribed maneuver. It's well choreographed. If you run this video from the paper, you'll see how well. I mean, they move, they stop, they rotate, and they move out. What is interesting, centralized algorithm was known to never gridlock, but I don't think anyone ever offered an explanation. Why not? So let me try to do that. Here, you have 2 cases, DFDR and PCCA. DFDR is known to gridlock occasionally. This is almost completely symmetric. There's just a little bit off. So you can see they are not going to unlock. And even if I put noise, nothing happens. They still stay like this. It's a stable configuration. In this case, PCCA, it's not stable. OK, but this is very complex, right? It's 24 states on the right. I can't analyze that. I can't even write a 24 by 24 matrix on a piece of paper. So what I'm going to do, I'm going to simplify this. Now, if you want something happening, you have to take out the degree of freedom. So this is 1 degree of freedom intersection. They decide the passing order, which one goes first through this intersection. They are very simple. x1, 0, x2, 0 initial conditions. They are negative, obvious. They start from negative numbers. v1, 0, v2, 0 are their desired speed. They want to move at that desire. v1, v2 are controls. I have standard CBF. And this one can think of this the same problem as negotiating the passing in a merge, right? Who is going to go first through a merge scenario? And adding second order doesn't change anything. It's another kind of fixed mode. So decentralized reciprocal, it's given here. I'm just going to give you equations for the decentralized reciprocal because I can write them down easily, right? So it's here. This is the solution. I keep different lambda 1, lambda 2 to make a point that making one more aggressive than the other doesn't solve anything. Lambda 1, lambda 2 is aggressiveness, right? When you are going to start braking, are you going to wait to brake late or brake early? Here, making those 2 differences buys you pretty much. I mean, one's less. The more aggressive one is more likely to go first. But other than that, does not solve the gridlock problem. Out of these equations, I immediately get that h of t always stays greater than 0, which is good. I guarantee collision avoidance. I can compute the eigenvalues. I'm going to skip the equilibrium set is this arc, right? You can see the arc. That's all these points when h equal to 0. You can see h equals 0 is equilibrium here and here. The eigenvalues are 0 and minus lambda 1 plus lambda 2. And you can, from 0, you cannot really conclude this in nonlinear systems. You cannot conclude much. However, you'll notice that this is because, well, take a look. Here, for example, you are here. I don't know if you can see my cursor. So you are there. x1, x2 are negative. This is a positive number. If h is not 0, this is a positive number on this side. So that gray region in that gray region, they don't go backwards. Once they get close to h equal to 0, they are stuck right there. That's why it's stable. And it doesn't matter if lambda 1 and lambda 2 are very different or the same. It's all the same. So just to show you some simulations, they would gridlock for offsets less than 0.25 with these settings. Here they pass barely. You can see they pass. But they don't go backwards. So if this blue was just a little bit ahead, it wouldn't pass. We ran the sweep in 2 parameters. You can see the results of the sweep. 60,000 points, about 15% gridlock in this space of V0 and X2. Centralized and PCCA. Centralized, this is the structure. I know positions. I compute for everyone. I implement whatever I compute. This one gives you a single equilibrium point there. And it's unstable. So it's positive. This thing is positive. It means this equilibrium is unstable. The only way you get gridlock is if you hit that line, measure 0 set that goes straight into the equilibrium point. Basically, that's why people think they never gridlock. PCCA, a little bit more complex, more eigenvalues. It now has these filters, but there is an unstable positive number. The same thing. And an interesting thing, 0 eigenvector move from physical to controller space. So the first 2 are physical, and the second 2 are controller values. Interesting observations. The faster they go, the faster they want to go, the more unstable the equilibrium is. Not the faster they go, the faster they want to go. Even if you start very close to h, they're going to move slowly. But instability does not depend on how close to h they are. It depends on how fast they want to go. And unstable mode is independent of design parameters. You can see that. I mean, there is nothing I can do with design parameters or there. Lambda and tau, which are my design parameters, have no impact at all on the instability. So PCCA simulation. This is the same thing as before, much nicer, obviously, faster. You can see here, well, you have to hit that. You have to hit the stable manifold right on. There is only one point that gridlocks. Now, this is one that wasn't in the paper, but it's often used. I can feed back what I observe in the other one does, and this is kind of in the game theoretic would be u minus 1 or minus I or a minus I, meaning what others are doing, not what I'm doing. So I optimize only for myself, but I take into account what others are doing, and this has to come with, because of the static loop, again, it has to come with some filtering or delay. This thing is unstable, but there is a pair of unstable eigenvalues. Right? This is Jordan form. This is the instability, but it's slow instability. To look at this, take a look at this one. They pass a little bit faster than this one. This one, but notice one thing. The red one was closer to the, and it's going to go second. First in, second out. That's not a good feature, right? But we observed it here, and this thing obviously it's much slower, and they would keep, if you let it run longer, this thing would go into the stable manifold. To summarize, I'm just comparing these what was observed on the right-hand side, observed gridlocks in 5 agents cases, and this 1D instability analysis, right? And you can see 0 gridlock if you say unstable. If you say stable, there are gridlocks observed. So there is kind of this theory explains why we have this. Another thing to observe, we don't know how to create these unstable algorithms. I did not know ahead of time that df with v hat will be unstable. We did not run simulation first. I did the analysis first. I said, oh, this is unstable. Let's run the simulation, see if it indeed gets 0. And indeed we did. However, you can see here, this first and second null has consequences. Well, this is what I just had, zero gridlocks. But take a look what they do. They are really reactive, too reactive, I think. This looks pretty ugly, I think. They are just trying to move out of the way of the other ones, which is not good, I think, for the speed of response. And again, I have some comments there, but anyway, this is details in all of this. But in any case, the theory predicted 0 gridlocks. We observe 0 gridlocks, aside from the reactivity, which is not related. Okay, some multi-agent unstable mode are undesirable. So I'm not saying, oh, just make it unstable and things are good. No. Number one, non-convex optimization methods produce discontinuous results, and people observe reciprocal dance in multi-agent systems. It's difficult to adjust to other agents' intent if the other agent keeps flip-flopping, right? If I say, oh, I'm going to go to the left, I'm going to go to the right, I don't know how to adjust to this. So here is simulation with a dynamic window, which is well-known algorithm. Discrete search, well, they crash. Humans do this too. Take a look. Left, right, left, they are going to crash. Well, the question is, braking was available all along, and they didn't do it. It was never optimal. It was a good thing to do, but for these algorithms, human as well as the dynamic window, it was never optimal. It was always suboptimal, and you use optimal. Assuming the other one is going to do what it was doing a fraction of a second ago, but you change your mind at the same time, and there's a little bit of computational delay. I forgot, 100 milliseconds compute or 200 milliseconds delay. Humans have probably 300-400 milliseconds delay. That's how you explain this. So anyway, basically this comes to the, I don't know, if you remember anything here, remember what I'm going to say in these 2 slides. Now, this is an intersection. There are 4 vehicles coming. There is no right-of-way, no communication, no intent preference, future trajectory info. They don't know what the others are going to do. They are both running either DF or PCCA. U0 comes from the simple trajectory follower LQR. This is bicycle model kinematic elliptical barrier. There are some constraints on steering, acceleration. There is a little bit of radius margin. Sampling time 50 milliseconds if you are interested. 4 vehicles, 2 go straight, 2 turn left. This one is the centralized follower. Everything symmetric. They are same distance, same initial speed, which is at the same time their desired speed. Take a look. I don't know why. Okay, you are not surprised that they gridlock, right? That's what we thought it would happen. Before I ran, I knew what would happen. This one is a more interesting case. It's not as intuitive. Low bandwidth, the same initial condition, same everything. PCCA in both cases, lower bandwidth on the left, higher bandwidth on the right. Low bandwidth, they pass nicely. Again, we expected this. I knew this would happen. Really nice, right? On the right, high bandwidth. Now they are more aggressive. They're going to start braking later. What happens is when you start braking later, you kind of brake too late. And then you have to untangle a little bit. So it's slower. Why? Well, I have an explanation. the unstable interagent mode is independent of lambda. You remember that. I said, well, that doesn't depend on my parameters. If I use smaller lambda, meaning lower bandwidth, I'm going to start breaking earlier. If I start breaking earlier, my negotiation starts early, my exponential instability kicks in earlier. If I start late, right? If you come from, this is really purely symmetric case, but I think asymmetry is added because of the solver, you know, rounding error or whatever. So you go from really minuscule, you need to get them into meters in some time. If you have a little time, you're not going to get there. If you have twice as much time, you may get there. That's basically the explanation. On the DF side, so for DF, decentralized Fowler policy on the previous slide, bandwidth did not play any role. That doesn't matter. That one does not have unstable equilibrium, and you don't observe any difference. So, conclusion, multi-agent system present a complex control design problem. Obviously, computational scaling, inconsistent info between agents because they don't know what the others are going to do. CBF is an effective way, in my opinion, and because convexity and continuity, and I said likely because I don't think there is a proof that actually is continuous. If we just observe it, it's a simple case, I said it's continuous, but in general, I don't know if it is continuous. With two agents, it's going to be continuous, while the other ones will not be even with two agents. If you remember anything, there are these blue things here, which I emphasized. Instability is our friend. It seems essential if you want negotiation, agent-to-agent negotiations. Instability is what you need, I think. We don't know how to create it. I don't have any way of creating an unstable algorithm. I could check. If you give me the algorithm, I say, yeah, this is unstable, or no, this one is stable. But I don't know. There is no parameters that would make centralized controller unstable. The only way, if you remember, the only way I could make it is make R negative. Doesn't make sense to make R negative, my radius, right? So it's like, that's it. It's stable because it's property of the algorithm. And finally, the last question is this how we do it? We would slow down, well, not in that video I showed you, but if these people actually did slow down, the two guys that collide, if they did slow down, they would actually negotiate. They would give themselves more time to negotiate a way out of this. Avoid the flip-flopping instability, which is the reciprocal dance. That's the end of my talk.
All right, thank you. I wondered if you would just say a word about, you looked at both holonomic and non-holonomic cases. How important do you think that distinction is? Does that really make a big difference, or in the end, not that much?
One thing that makes a big difference, I have a slide here that says, even if the other one was non-cooperating, just going through, you can still have O of delta t kind of error. Mm. This is true for holonomic because you can move sideways. Oh. If it is non-holonomic, that result does not apply. A bunch of other things do apply, but not that one. And the reason is, if it's coming from the side towards you, you are not gonna, the natural thing would be you move out of the way like this or like this, but you cannot move sideways. So you are going to actually get hit. Yeah. If it is holonomic, you can move sideways because that's just y coordinate you control. So you would move, and then I have in another presentation, I have a nice video when one is chasing the other. One, assume I can show it to you if you are interested. But one is chasing the other. But the other one is not aware of this. It thinks the other one is running PCCA and they are all cooperating. Still, the one with PCCA, because there is large disturbance coming, like the W is large, it actually always accounts, and they actually chase one another around and colliding just a little bit. So this, as the result says, they would. But that's true only because the the holonomic agent cannot be broadsided. Broadsiding is the problem, right? You have, see, continuous controller. That's a bad thing about continuity. That's why I think we humans have both switching as well as continuous part capability. But if you sit there and you only have a continuous controller and it comes straight to you from the side, see, if it's going to hit you in the back, you're going to move forward. You're going to hit in the front, you're going to move backward. Continuous control has to have 0 somewhere in between moving forward and moving backward. Because it's continuous, there has to be 0. 0 means you're going to get hit because you're not going to move. Your controller says, don't move. I mean, because it's continuous.
Yeah.
That's why I think as humans we have both. And these guys, unfortunately, turned the switching one. Which was unfortunate. I'm not saying the continuous one is solution to all the problems. Obviously, if you're going to get broadsided, you won't turn this continuous one on.
Go ahead, I'll give you this so you can get recorded.
Great, I'm having some continuity between like the last seminar I saw and this one, the first I'm seeing of this year. So in the last seminar I saw of last year, we were actually talking about traffic circles in Indiana and some of the impact that had on improving traffic flow by moving to that. And one of the things that they had to do was they had to give preferential right-of-way to trucks, because trucks might have to occupy a couple of lanes in order to prevent gridlocking. And so thinking about that and thinking about your talk, I'm curious about sort of, both potentially how this would extend to geometries like a circle, which was also one of your initial motivations, but also just more broadly how this might work with asymmetric actors where, I have, for instance, a lot more size associated with the truck, or I have slightly different motion constraints.
Right.
How that might impact some of these results. Is the sort of symmetry among actors beyond their actions potentially important in these conclusions?
I don't know which one you want to look at. Let's say this one. Let's say this one, actually. You have here the minimization for all, and the weights are the same. If you have one of these J's, or even the ego vehicle could be the truck, right? I say, well, it's much more expensive for me to change my preferred thing than for other ones. You still enforce the constraint, so they are still going to stop if they can, but the cost inside is going to be much more expensive if I do something than if the other ones do. If we all agree that the truck should be weighted by a factor of, let's say, 10 or 5 or whatever the appropriate number is, then everything's going to work fine. Even if not, even if we disagree on the weights, this thing, at least in this holonomic case, is going to be okay, because it adjusts to whatever the other ones are doing. Basically, even if you put 5 agents and one of these 5 is not an agent, you're just plowing through, right? They are still going to have O of delta t violation, because the other ones will realize that something's wrong, and they would move out of the way. And I have simulations that show that. As I said, one was chasing the other, and they would move. Again, non-holonomic, you lose a degree of freedom if you want.
Yeah, thanks. That comes through very clearly.
Thanks, everyone.